Hello, everyone. It's really my pleasure to present our work, Slicing Through Bias, explaining performance gaps in medical imaging analysis using slice discovery methods. And this is the work that first also is our student Vincent, who is unfortunately not be able to attend this year's impact. And then we also, this work is also collaborated with Olesen and Ika. And then before everything starts, I just wanted to report the last slide from Murthy's talk that because I feel like it fits perfectly with what we're working here, because this work is definitely starts with like we find out that things doesn't work and we look into why things don't work, and then this paper is about how like a potential methods that might help us to figure out which spot that things doesn't work. So to start with, that we usually in medical imaging or in other domain that we have an AI model that will which is under evaluation, and then usually we'll use some sort of metrics to evaluate it, like the accuracy, the areas under the graph curve, and then sometimes like I'm sorry about the emoji there, but it should be a little bit prettier. But sometimes it will give us quite high performance, and then we are very happy about that. But the thing is that the model might work significantly better for one subgroup rather than the other subgroup. For example, one gender compared to another gender, a type of scanner compared to another type of scanner. But sometimes it doesn't work when it comes to a rare demographics, or it might fail when it learns the shortcuts rather than the real disease. So that means that the average tested performance doesn't really mean that we can conceal any problem. So that and sometimes that even if you have some suspicious, or like for example there's something to do with the shortcuts, but you have to be very specific about it, and then using some actual labels to deal with the problem, so you can only address the problem that you already know. So, and then another motivation is actually coming from this paper, Gender Imbalance in Medical Imaging Datasets produced by Classifier for Computer-Aided Diagnosis, where they find out a very interesting thing that while we train a classification model to predict pneumothorax through chest X-ray, there is a very significant difference in terms of performance in different gender groups. And this is like we see this, and then but we don't know. We actually don't know why this happens. So we do some sort of hypothesis and try to investigate into it. The first hypothesis is that women underrepresented in our training set, but this turned to be not be the cause, because when we only train with female data, men are still outperformed. The second hypothesis comes from the nature of when you take chest X-ray, there will be a breast shadow for women, and it might be something that reduces the image quality in a chest X-ray. But we do a test that we just crop the second half of the image. So ideally, it shouldn't represent any like breast formation in that sense. And then, of course, the performance reduced for all the cases as part of the information is lost. But the trend is still exists, like the men still outperform the female. So this sort of testing is done by the paper under there, which is in last year's FAIMI. And then that leads to an important question, like how can we identify the loopholes of observed performance disparity in machine learning or in like AI, right? That's the solution that we want to propose in this study. That one of the solutions could be what we call slice discovery methods. And here we need to mention that the slice means a subset of your data set, because we have, of course, another terminology in the 3D volume data, like if you present like they call it 2D slides, so we want to distinguish from that. So how does this slice discovery goes? Usually there will be three main steps in slice discovery methods. The first is that we will do the embedding. So we have the images and then or other data modality, we embedded them into some highly dimensioned space, feature space. And then we'll reduce the dimensionality using some methods. And the third step is that we're trying to cluster with the features that reduce that after the reducing the dimensionality. And as we can see here, after we cluster data, we'll try to find out the high or low performing clusters, and then we try to figure out what is happening in that cluster. So in previous studies, like there are different methods has been implemented in these 3 steps. And for our methods, we suggest that we do things as follows. Like for embedding, we're going to take the second to the last layer of the model, and then so that's this compared to other methods. For example, some methods use the features from a pre-trained model, like constructive learning model, like Click. Or by using this, we can actually use the information that is related to the model. And then for the dimensionality reduction, we use a 128-dimensional fully connected layout for that. And then that is like we can also take the label information into account, and then with respect to other methods, it can take that part of information. And then we use the Gaussian mixture modeling for clustering, and then we use the Berry tool for selecting the high-low performance clusters. So this for just to be brave, this takes both the accuracy and calibration into account. So and then this thresholding independent. So it's a little bit better than like using accuracy or using the errors under as well. So for the experiment setup, we look into the NIH dataset and check for dataset, and then our check, and then we need some annotations of the chest strain, and then it's from this paper, the first paper here from Ronka and Miller's group, and then we using only 1 sample for patients with a preference for pneumothorax positive samples with an equal sex ratio, and then we reduce the this step is for reducing the potential impact of the data noise. And then we also put the data sets into prime validation and testing. And then we use ResNet 50 as our model. And then we also use some data argumentation. So here we show the results. So for the NIH data sets, here we show the results of the worst performing slides and the best performing slides for pneumothorax positive cases. But you can see that when there's no drain, no chest drain, in the pneumothorax positive cases, it performs worse. And then when there's with drain, that it performs better. It indicates that the chest drain might be a very important factor in terms of predicting pneumothorax. And then this sort of indicating the shortcut learning problem. So, and we also want to mention that this is previously reported in the literature in your right corner. Okay, and then about the results for check spreads. Here we're also looking at pneumothorax positive cases, and similar trend also happening here that when there's no chest drain for pneumothorax positive cases, it performs worse, and then vice versa. And then for pneumothorax negative cases, it shows in the output of like basically the same story showing the same trends. And then we try to see if it is really because of the chest drain. So we do this test here, and then here we show here. So I forgot to say that for Burroughs score, like the lower the better. So you can see that if you're with the drain, and then in the if you're without the drain in the pneumothorax positive cases, then the score is higher, meaning that the performance is actually worse. So we also do a test, like we balance the data set, but here is for the check score data set. So you can see that for the green box, it is before we're doing anything in the original data distribution, and then you see the performance difference amount gender, and then when you balance it with the chest drain, and then the performance becomes sort of like similar, and then also better focus. So this is also not technically a proof of the shortcut learning. And in terms of like how can you do it, like in the more restrict cases, we propose another method which is presented in CCP. And if you're interested, you can look into that. So with that, I will conclude that here our contribution is that we provide the more class discovery methods, and then we also review that the shortcut learning double check like it is caused by the chest drain or the ECG indicators. And then for other details, you can look at our paper. Thank you.